Look around you. Everything in the universe, from the tiniest atom to the most distant star, has a size, a weight, a duration. But how do we capture all of that in numbers? How do we measure the universe? From the size of an atom, to the distance of the stars, measurement is the bridge between what we see, and what we truly understand. Imagine two ancient builders. One measures in cubits, the length from his elbow to his fingertip. The other measures in feet. They build the same wall, but their numbers never agree, because their rulers were never the same. For centuries, this was the problem. Every village, every kingdom, measured the world differently. So the world came together and agreed on one language of measurement, the International System of Units, or SI. One language. One system. One world. And it rests on just 7 base units, the 7 pillars from which every other measurement is built. Let's meet the 7 base units, the foundation of all measurement. First, the meter, the unit of length. 1 meter is the distance light travels in a tiny fraction of a second. Next, the kilogram, the unit of mass, now defined by Planck's constant. The second, our unit of time, is measured by counting over 9 billion vibrations of a cesium atom. The ampere measures electric current, the flow of electric charge through a wire. The Kelvin measures temperature, anchored to Boltzmann's constant. The mole counts particles, Avogadro's number, more than 6 times 10 to the 23rd. And the candela measures luminous intensity, the brightness of a source of light. Every measurement carries a little doubt. The digits we trust are called significant figures. Look at this ruler. It reads 2.5 centimeters. The 2 is certain, but the last digit, the 5, is our best estimate. On a digital scale reading 4.700 grams, even the trailing zeros count, because they show how precise the instrument is. We can write large numbers cleanly. 4,700 meters becomes 4.700 times 10 cubed. And when we divide measurements, the answer keeps only the fewest significant figures. 4.237 over 2.51 gives 1.69. The last digit is always a guess. And that is honesty in measurement. Every physical quantity has a hidden identity, called its dimension. Length we write as L, mass as m, time as t. A cube has volume, which is length times length times length, so its dimension is L cubed. A moving car has velocity, length divided by time. Speed up, and you have acceleration, length divided by time squared. Push on a mass, and you get force, mass times acceleration, written mLt to the -2. Here is the golden rule: you can never add two quantities with different dimensions. You can't add apples and oranges, and you can't add meters and seconds. Dimensions are the DNA of physics. Because every term must share the same dimension, we can build a machine that checks any equation. Feed it 1/2 mv squared equals mgh. Both sides have the dimensions of energy. They match. The machine flashes green. Correct. But feed it k equals m squared v cubed, and the dimensions simply do not agree. The machine flashes red. Wrong. Remember this carefully. An equation that is dimensionally correct might still be wrong. But an equation that is dimensionally wrong, is always, completely, dead wrong. Now watch the power of this idea. Here is a swinging pendulum. What decides how long it takes to swing? Its length? Its mass? The pull of gravity? Using only dimensions, we can reason it out. The period depends on length and on gravity, but, remarkably, the mass cancels out completely. It simply does not matter. Dimensional analysis hands us the form of the answer, t equals 2 pi times the square root of length over gravity. Dimensions gave us the form. Experiment gave us the number. Together, they gave us the truth. From the size of an atom to the distance of the stars, it all begins here, with measurement. Master these tools, the 7 base units, significant figures, and dimensions, and you hold the first key to all of physics. If this helped you see the world a little more clearly, subscribe for more content. Keep wondering.